How's everybody doing this afternoon? All right, pretty good session, our summit so far? Awesome. Okay, great. So we're going to get started here. My name is Gavin Adams, and I'm a solutions architect with AWS. I've been with AWS now for about 3+ years, and my specialty is on IoT, meaning that I focus strictly on IoT opportunities or workloads customers are doing. And so in this session today, we're going to be doing IoT building blocks, essentially going from edge devices, physical assets, all the way to doing analytics into the cloud. So it's a quick agenda here. First thing, we're just going to do a quick level set on IoT. Who in here has actually done an IoT project? Awesome. Who in here has never even worked with IoT and you're coming here just for the interest? Okay, great. So there's a good mix there. We're going to do a quick level set on what IoT is. Then what AWS's approach is to helping enable customers complete IoT solutions. And then finally, we're going to do a deep dive into the service portfolio. These are the building blocks that help you get from the edge all the way through analytics. So what you'll come out of from this session, if you stick through it with me for the next 45 to 60 minutes, is an understanding for all the different aspects in context to a particular use case that we'll come up with at a general level, understanding where you apply different things. What we won't actually do in this session is go into a deep dive into any one area, with the exception of the IoT core, and there's a couple of reasons for that. So let's just talk about what a thing is. A thing in characteristics of a physical device has got some characteristics that are pretty common. You have to be able to sense the actual world. So this is going to be sensors. It could be humidity, temperature, accelerometers, things that allow it to actually sense what's happening inside the world around it, or to actually act upon it, or to actuate, take control. There's going to be limited resources. These may be CPU-constrained devices, it might be memory, or some other type of resource that doesn't give it sort of the full capabilities of a general-purpose compute platform. It has to be able to operate in isolation. Because it's out there in the world, we're not going to have great connectivity all the time, and so when it doesn't have connectivity to the cloud or to IoT, we want to still be able to have that device operate, potentially collect data, buffer it, and be able to send it back up. And finally, it has to have some way to communicate. And if you notice here, we actually talk about firmware with connectivity, but we don't actually call out internet. We don't call out TCP/IP, because depending on the particular device, it may have communications in different ways. So for today's session, we're going to go and focus on a very important device, the toothbrush. And we're going to talk about a IoT-connected toothbrush. And if you imagine, this can actually happen a couple different ways. It could be a giant, bulky device that has got full capabilities, Wi-Fi, the connection directly to the cloud, or it might be something that's a lot more constrained in regards to that only has maybe like a Bluetooth low energy connection that then is in turn using a companion app on a mobile phone. And you see this a lot in the consumer space right now, Fitbit or other devices that are collecting and sensing data, then they're using an actual higher processing power and capabilities on an actual mobile app. So the two together, a mobile app and a physical device with something such as Bluetooth connectivity, will allow for that to happen. So this is basically what our definition of a thing is. So what's the Internet of Things? Simply put, it is those things that are communicating to a common platform in the cloud and are interacting either with each other or with back-end services or workloads. So this could be talking to back-end order management systems, sending up telemetry data, predictive maintenance. There's a whole bunch of different use cases from here. So that's pretty much our definition of what we're going to talk about today, Internet of Things. So if we put this in the context here of what does this mean from an AWS perspective, is that we look at it in 3 different approaches. The first one is going to be those physical devices, things that can actually sense and act, things that we can actually touch and interact with. And there's a different set of building blocks we'll use around that. There's also going to be the cloud component. Because devices are constrained, there's a lot of things you may want to do with devices and the data that is more appropriate for the cloud. This could be the ingest of millions of devices of sensor data. It could be doing analytics on the back end and then sending back insights or results to our physical devices. Sum that up, overlay the two with that intelligence. So the ability to get that data from things or to things, perform those operations in the cloud, and then essentially have insights or intelligence that we can take and perform upon these devices. The way we break this down in AWS is in 2 different categories, things and cloud components. So we're going to start talking about the things themselves, how we actually connect to the cloud in a secure manner, publish messages. We'll go into detail in regards to the capabilities of the gateway or those edge devices. And this can either be with AWS Greengrass, which is our compute at the edge, or with Amazon FreeRTOS, which is a microcontroller operating system for constrained devices. From the cloud side, we're going to talk about secure connectivity, messaging, how to manage your devices at scale, how to protect your devices once you do have them at scale. And then once you're having the data flow through in a secure and controlled manner, how you can actually take insights upon this. So first, we're going to go and do a deep dive into that secure device connectivity and what we call AWS IoT Core. And AWS IoT Core will provide these 6 capabilities. The ability to authenticate what the device is, allow connections for the devices or the things, publishing and subscribing for messages, acting upon those messages from the rules engine, interacting digitally with a virtual representation of the state of the device, and then having additional metadata or information in regards to what the device or your fleet of devices looks like. So let's start with the identity service. And for anybody that's playing AWS Bingo, I'll throw you up the first one here, is that security is job 0. This is very critical from everything, but especially when you're talking about IoT devices where they're out in the world and you don't have full control over them. So we actually enforce that every device that connects to the platform has to do so in an authenticated manner. And it's also our best practices from a well-architected perspective. The way we do that is things can actually present digital certificates to say, here's who I am. So locally in the device, in a secure element store, hopefully, is that you have your certificate and a private key, which allows that thing to connect to the platform and say, here is who I am, and that the platform itself or the cloud can say, okay, I trust who you are. These can be certificates that are issued by AWS, or you can actually bring your own certificates or your own certificate authorities to accomplish this. There's things inside the cloud, but it doesn't mean that they're actually having to be registered or provisioned when you're making the connections. So we actually have the capability of doing just-in-time provisioning or just-in-time registration of devices. So imagine a device is manufactured in China, a digital certificate is put onto there that's trusted. The first time that device actually connects to the platform, that will trigger off a process which will do the registration of that thing as a representation inside of AWS IoT, attach policies to it, and then allow it to connect, therefore alleviating you having to do that process up front. Once somebody is identified, we then take the credentials or the principal for authentication and attach that to either IAM, Identity and Access Management, or AWS IoT policies. So this allows a device or thing in the field to have capabilities to interact with AWS IoT from an IoT policy, and potentially with other third-party or other AWS services such as S3, Kinesis, et cetera, by using a standard IAM policy and credentials. You can also use Amazon Cognito user pools as principals for connection to AWS IoT. And this is a great use case, coming back to the toothbrush again. Companion app, you log in and authenticate with the username password. In the back end, the SDK will then grant you or vend you the permissions to interact with the IoT platform. And for those that actually want to use your own identity provider, you can also use federated identities or the Cognito identity capability to do the same thing. So we have our toothbrush. Let's say this got a certificate on there. We've got a valid connection to AWS IoT. The next thing is that once we've got that connection and we know who we are and our permissions, we're asked to actually be able to publish and subscribe messages. So first of all IoT connections are long-lived connections. And we'll go through basically through the protocols of how that actually is accomplished. MQTT, or message queuing, telemetry transport, is essentially one of the common ways to do this. It's a lightweight protocol that allows you to publish and subscribe messages across the platform. However, if you also want to use WebSockets, totally doable. You can use MQTT over WebSockets. And then also for other operations, you can actually use HTTP for doing posting or putting of information, such as just doing a straight publish when you're not having to do a subscribe. All of these will then support basically the different authentication mechanisms that we talked about. So we talked about X509 certificates. So that's normally used when you're talking about MQTT connections. Signature v4, or the standard signing process that we use at AWS across all of our services, is used when you're doing those WebSocket connections or doing MQT over WebSockets. You can also use your own custom authorizer. So if you have a platform out there that's already vending JSON Web Tokens or JOTs, you can actually put your own custom authorizer in place to actually support that too. Key thing is, and again, from the bar of security, we enforce that every connection has to be TLS 1.2 or above. Currently, we support TLS 1.2, and that was a constraint or a concern back in 2015 when AWS IoT first came out. But we essentially want to ensure that we're not using any type of protocols that are either insecure or may have vulnerabilities that could be exposed. And as TLS 1.3 and other protocols mature and become available in SDKs and for platforms, we'll continue to adopt those also. So we've authenticated our toothbrush, we've connected it. We now actually want to emit messages. So we might want to say, what is the sensitivity or the pressure on enamel, battery life, these types of things. This is going to be used in the message broker, where we scale out and essentially are going to be publishing and receiving messages from the devices. The standard mechanism is a pub-sub model, so that a device will connect to the platform and it'll publish a message. It can also subscribe to a particular topic in which if other devices or applications publish messages, it can then receive those and act upon them accordingly. This is all on top of MQTT, and we support quality of service levels 0 and 1, which basically means that you can either use 0, which essentially is at most, or 0 or more times that a message will be published, or quality service 1, where it's going to be at least once to be published. Meaning that, and there's different use cases for this. If you're streaming up a lot of telemetry and you don't care if you miss a message here or there, QS0 could be a more appropriate mechanism. It's also a lower cost because you're not having sort of the publish and the publish acknowledge messages coming back. But there are use cases where you might want to use QS1. We provide you that capability. Now, topics are a standard structure inside of MQTT, and just like a lot of other publish-subscribe mechanisms, it's a hierarchy. So you start at the top, which could be something such as telemetry / device name / sensor name. And you can actually publish or subscribe to any of those levels or to a wildcard on those particular levels. And besides being able to publish to the wildcards, we also have reserved topics. So these are the ones that will start with $AWS / and the hash here essentially means it's a wildcard for everything that's lower than that. And these are where we'll actually interact with other portions of the AWS IoT service in regards to shadows, lifecycle events, these types of things. So now we're getting messages flowing back and forth. We're having our fleet of toothbrushes sending back in events on battery level, individual personality of how people are brushing. And I actually want to take action on this. If this is going into the message broker back and forth, there's no real value here. So we actually bring into here is capability in the core called the rules engine. And when you create a rule, you're basically saying that using a standard query language, SQL-like, is that I want to act on certain messages, on certain topic structures, and that I may actually want to only interact on certain ones. So in this particular case here, is that we only are interested in messages that have got an attribute of temperature where the value is greater than 35. So if the rule is in place and a message comes through temperature 34, it'll see the message, it won't act upon it. But as soon as it actually sees that go above that, we then have what we call actions. And actions are downstream AWS services, and these can be such as Kinesis Analytics, S3, DynamoDB, SQS, SNS, etc. Or it could also be third parties for the likes of Salesforce.com or here.com, which can support the ability to send messages out to their services for ingest directly from AWS IoT. A couple other capabilities of the rules engine is also to republish messages. So you can actually get messages in on one topic and republish it to another topic. Good use cases here, you might want to send it over to a debugging environment or send data downstream for doing development purposes. You can also do, which is round trip. So a normal rules engine will take in a message, do some type of transform or verification on it, and then send it downstream. You can also send this to a machine learning model where you're going to get back basically a probability, and then you can act upon that. So if you imagine like a binary classification where is this temperature probe about to fail? I send all the data up to a machine learning model inside the rules engine. That particular rule gets the responses back, and if it's a 0, false, we're not going to fail, or it's a 1, yes, we are going to fail, it can take appropriate action that way. And again, you craft that all into these SQL-like statements. Device shadows. Probably one of the most powerful capabilities of interacting with things is because you got basically two things. You got physical devices that are out there that are going to have intermittent connectivity. Sometimes they're going to be on, sometimes they're going to be off. You're also going to have applications on the other side that want to interact with your fleet of devices. But how do you do that when 20% of your devices of, let's say, 1 million are offline? And we do that through what we call the device shadow. The device shadow is basically used for the state and the continuing changes of a state of a physical device. So imagine in our toothbrush, one of probably the key capabilities is going to be battery level. It may want to determine what the battery level is, or if it's currently activated or off. And what you'll see is that it'll basically be a JSON document that'll have two different components, a desired state and a reported state. Devices are normally going to publish or update their shadow document, which is in the cloud, with the reported state components. So battery level, 95%. Conversely, you might have applications that want to read across all of the devices, what is the average battery level? Well, if there's devices that are offline, it won't be able to access those. But if the application works with the shadow, it'll be able to read all those values from the last reported state and be able to take action. And as mentioned, the key thing here is to make it easier for applications to interact. Shadows are an always available service, meaning that when an application makes an API call for shadows, it's always going to get a response. Conversely, if you have applications that need to talk directly with the device, you may need to poll, is the device available, wait for the device to respond back, and then act upon that. So a quick example of the device shadow. We have our thing, we have the shadow in the center, and we have an application on the right-hand side. Device comes online, it's got an LED or some type of indicator, it's blue. So the first thing it's going to do is actually going to publish that its reported state for that color is to blue. Now an application can actually poll the shadow and say, what is the current color? So it's actually going to poll and look at that reported state, because that's the last time that the device actually reported something. They'll get that color blue back. We don't like blue. We want to set it to red. So the application, instead of actually writing directly to the thing, is going to update the desired state of the shadow document to red. But our device isn't online. It's still showing blue, time is progressing, and finally the home Wi-Fi or whatever connectivity comes back up again. So when the device actually reconnects to AWS IoT, the first thing that's going to do is going to say, oh, I've got to reconnect, I'm going to read that shadow. I've got a new desired state that I need to update. Locally, it changes its color to red. When it's verified that its local sensor or device has been set, it's then going to publish back up to its shadow document that its reported state is now red. And again, if an application then reads that current color, it's going to read from the shadow and get red. So essentially decoupling the connectivity of a thing or an application by using that intermediate state of the shadows. And then finally, we're going to talk about the registry. So the registry is where you can store static metadata on different components. This can be on an individual thing, a type of thing, or even on groups. So if you imagine that some of the static metadata may be things such as serial number. It might be the date of the firmware that was first published, a SKU number, model number, things that are never going to change, but that you may want to downstream, and we'll talk about this, is do some queries or interactions on this. To make it easier, we have a thing called a thing type that allows you to take different attributes by naming convention and make those available as a single thing type that you can apply to a variety of things. In the toothbrush example, it might be serial number, firmware version, and particular SKU number. We have a production run of 100,000. They have this. We design a new toothbrush. We'll create a new thing type to reference this new toothbrush for all the new things that are created underneath that. You can also group things together from a registry or metadata perspective so that you can essentially act upon a group of things that have got some common attributes. So these can be applied to a group, which then in turn are sort of inherited by things when you do queries or want to take actions upon those. And then when you have these devices in groups, you can now apply jobs to them. And what jobs basically allows you to do is to set an action that you want to apply to a discrete number of devices, say 10,000. We're going to do a firmware upgrade. Every one of those devices will get a job document with the components of where they actually get their upgraded firmware, S3 pre-assigned URLs. They can then perform their operations and then report back what succeeded or failed. From your side on actually doing this deployment, you can see the progress of how many devices have completed and also the composition of success to failures on those devices. So that is secure device connectivity, which we call AWS IoT Core. So let's now go over toward the edge and talk about AWS Greengrass. Has anybody here worked with AWS Greengrass before? Okay, just a couple people. So AWS Greengrass is a piece of software that you download that runs on physical hardware that you have. So this is going to be on an x86 or ARM-based processor, essentially Linux, and it will extend some of the capabilities that we have in the cloud down to local devices. And the main reason for this is that there are times where you don't want data to actually ever leave a local environment. Think of jurisdictional or regulatory domains, healthcare, things such as this. It also might be that you're doing such a massive amount of messages. Let's say it's thousands to hundreds of thousands of messages per second across the fleet of local devices. You don't want to have all those charges going up to the cloud and potentially coming back down. And then also it's based on time. If you need to get responses in milliseconds or seconds, the cloud's an appropriate environment. If you're in an environment where you need to act on something immediately, microseconds, or even faster, things like autonomous vehicles and LiDAR and automatic braking, you want those types of interactions to happen very close to where the events are being generated. So the first thing that Greengrass brings is that MQTT broker down to a local environment. So now devices, instead of having to connect all the way up to the cloud, are connecting to a local Greengrass core, and they can now send messages back and forth. The triggers allows you to also take a look at certain topics and say, oh, if I see messages coming in this topic, besides going back and forth, I also want to emit those to the cloud. So it's a mechanism for having not just sort of east-west traffic between devices, but also that north-south traffic from devices or a Greengrass core back into AWS IoT Core. Local actions, and this is where AWS Lambda comes into play. You can actually create Lambda functions in the cloud and then publish those that are then pushed down to the Greengrass core and run locally. Very powerful. So in this particular instance, you can actually have a local inference, maybe from machine learning models that are running locally. The messages coming in are from a video camera or something such as this. It's taking some action, and then it may actually emit messages to other local Greengrass aware devices to take some particular action. And we support a subset of the languages inside of Lambda. And then recently, in the last couple of weeks, we've also added support for binary C and C++ applications to be put down locally, which is great because it gives you a lot more performance in constrained devices. That shadow capability that we have in the cloud is also pushed down locally, meaning that we can essentially sync changes on the shadow from a local Greengrass environment up to the things representation inside the cloud. That same security model that we have in AWS, where we enforce that everybody or everything must identify themselves, TLS 1.2, so data in transit encryption, are all enforced at the local level. So we actually state that any device that connects to a Greengrass core must have a client certificate, and it also must validate the server certificate that's running on Greengrass core itself. Internally, inside of Greengrass, we also apply the same permissions models where things such as Lambda functions or other capabilities can also have scoped-down identity and access management policies or roles for what interactions they can have both locally and also up to other AWS services. Another thing that Greengrass provides is local resource access. So you can now actually access the local file system and essentially anything that you have in the /dev, all of your devices. I mentioned the video camera. Greengrass or the Greengrass Lambda functions can have direct access to those particular resources. If they're not granted access, though, they're not going to be able to actually access them, and again, enforcing that security model. Machine learning inference. And has anybody worked with deep lens before? Okay, a couple people. So deep lens basically is a reference architecture for how all of this works with Greengrass. But it allows you to take a machine learning model that's trained in the cloud, deploy it locally inside of Greengrass, and it runs as a long-running or continuous function that you can then do inference. Again, it may be something such as object detection. Do I see a hot dog or not a hot dog? And then basically publish a message, either locally to devices, saying, please don't eat my hot dog, or up to the cloud saying, yay, I saw some hot dogs. So again, it's the ability to have machine learning models, and you can basically train anything that you want using your Jupyter notebooks and SageMaker capabilities that runs locally. We also have the protocol adapters, and this is essentially the ability to interface with the Greengrass environment with what's commonly known as sort of brownfield or other environments. If you're in the industrial space, this might be that I want my Greengrass MQTT TCP protocol to talk with Modbus or Modbus TCP or Profinet, or name your protocol that's out there. So we have actual reference architecture for how to design protocol adapters to interface with these other non-Greengrass environments, do the translation of messages, and then be able to publish those back up and act upon those with local resources and local actions into the cloud. Greengrass also supports the ability to upgrade itself. So as we come out with versions such as 1.3, 1.5, and recently 1.6, you can essentially initiate an over-the-air update, which will download the latest version of Greengrass, do a restart, verify that everything is operational, and if it is, great. If it isn't, it'll roll back to the previous version and give you the debugging information that you need. So that is one portion of the actual physical devices that we're talking about, Greengrass. The gateway that gives you that capabilities, but again, it's something that you're physically touching and working upon. Now let's talk about endpoints, and there's two different approaches here. The one at the bottom is going to be something that's going to use a native protocol or native adapter or SDK, such as an MQTT library, to connect to AWS IoT. And any of the standard ones out there for operating systems will have things such as Paho and others that allow you to do that. But we also have something called Amazon FreeRTOS. Last year at re:Invent, we announced this, that we took over the leadership of the FreeRTOS project. And FreeRTOS is a very popular open source real-time operating system. And on top of that, we created Amazon FreeRTOS, which extends the capabilities of the base RTOS that embedded developers use today to provide the capabilities to easily start to interact with AWS IoT services. We provided local connectivity libraries so that we can essentially be able to send messages back and forth to different types of connectivity endpoints. Imagine, again, Bluetooth low energy, that we want to be able to talk to a near-connected device and get messages back and forth. There's also connectivity to the cloud, so the ability to have connections either to Greengrass itself, and we call this a Greengrass Aware Device Connectivity Module, or AWS IoT. So the ability to essentially say, do a connect, give it an endpoint, give it credentials, because we need those, and in the background, that particular library will handle all the connections, reconnections, retransmits, the publish and subscribing of messages. Security, again, is the ability to expand or extend the capability for security out to other environments. So we do support standard TLS libraries that are built inside of FreeRTOS, and Amazon FreeRTOS, and also the capabilities for third parties to extend this if you want to use things such as secure elements to store and retrieve credentials from that aspect. And then finally, and this is still currently in beta, is the ability to an over-the-air update where you've got your application that's running, you've made some changes, you recompiled it, you now have the firmware, you upload it to S3, you initiate a job, which will now send that actual new firmware down to the devices. And actually uses MQTT for that to essentially stream the download until it's complete, and then essentially do a reboot to verify that it's operational with the new version of your firmware. And again, the capability of doing rollbacks in the event that you do have a failure. So that was the actual devices there. So we've talked about essentially the core components of the cloud and how we do the connectivity and scaling messages. We've talked about all the aspects of how you have physical devices connect. So now let's talk about once you have, instead of one toothbrush or a pilot of, let's say, 1,000, what happens when you scale to having millions of devices that are out there that are doing billions of messages? And from that, we have AWS IoT Fleet Management. And this brings some capabilities to actually manage the health and well-being of that fleet of devices. The first one is batch fleet provisioning. This is a very common practice in manufacturing where I'm going to generate 1 million toothbrushes. So I'm going to generate 1 million certificates, put them onto a file, send it over to my manufacturing facility, where they're going to embed those certificates, unique for each one. But now I need to provision 1 million devices. Before, we'd actually have to do this through an API process of, create a thing, create a certificate, attach these things together. We now have a fleet provisioning process where you can essentially create one manifest file with all the characteristics that you want, send it up, and in the background, the platform, our IoT device management, will do the provision of those devices for you. Once you have the devices in there, and we spoke about that metadata inside the registry, but also the shadow information that's inside each of the things shadows, you now do basically full real-time indexing and fleet searches across this. And this uses a standard Lucene language where I might say, provide all toothbrushes of this particular SKU that were created at this manufacturing date with a battery level less than a certain percentage. And the response back will be that subset of things that exist out there. Another thing is that now that once you can start to group things together in groups, is you can now apply fine-grained logging. In the past, we had essentially switched to, would say, turn on logging for informational or errors all the way down to debug mode. But that's across everything. If you imagine you've got 1 million devices out there and you put it into debug mode, you're going to get a lot of CloudWatch events that are being published. So now you can actually do this on a particular device or on a group. So imagine you've got a logging group. You can bring one device over into that group, only have logging turned on to there for full debug, get your aha moment or fixing this, and then put the device back into its regular thing where it's only alerting on warnings or errors. And then finally, device management essentially automates that process of having the groups of things and the jobs for doing those over-the-air updates. So the ability to provide a piece of code to S3, and then the actual job service will then generate pre-signed URLs for each of the things, send it down to them, allowing them to actually go and download their particular firmware directly from S3, apply the updates, report back with that success and failure mechanisms again. So fleet onboarding or fleet indexing components here with device management. All right, so we now have a fleet of devices. They're sending a tons of messages out there, and they're scattered across the world. We actually want to take care and ensure that we are managing the security of those devices once they've been deployed. And from this, we have our Device Defender. Who attended the Device Defender session today? All right, so you know that coming in 2018, we're now in 2018. So it was released today and is now generally available. And what Device Defender does is it gives you some capabilities to essentially audit your devices. So this may be things such as certificates that are about to expire, devices that may be sharing a certificate, which is an anti-pattern, but essentially be able to get back an audit configuration for devices that are in compliance and ones that are not in compliance. It also can be that you can now set up audit behavior or monitoring device behavior. So this might be that you want devices that are being issued, let's say, to a particular region, let's say to China. Well, you can put in things such as source IP addresses. If I see these come from China IP address blocks, I'm going to whitelist these. These are good. Or if I see these coming from another region that I don't expect them to be, I may want to blacklist them. But you can now start taking a look at different characteristics on the physical device of where it's at, how much messages or throughput it's doing, other types of characteristics, and start to actually monitor and track those particular behaviors. Based on both the audit configurations and that device behavior, is then you can actually identify anomalies. And you can put these against different things such as are these low criticality or low to critical type of issues, but essentially know that, all right, I'm suddenly seeing certain devices that their certificates are about to expire, or devices that have moved into a region that I'm not interested in, or that they shouldn't be over there. And from there, you can actually generate alerts. So from an SNS topic, these can be sent downstream to any type of SNS subscriber or simple notification service, where they in turn can then act upon these. Normally, this would be like the invocation of a Lambda function that will take in a message and say, I've got a particular devices or two devices I'm seeing with the same certificate. I'm going to take some action and report to somebody saying, hey, take a look and see what's going on here. And then again, based on all of that context, this allows you as a developer to essentially identify where vulnerabilities may exist because of past behavior, and apply patches to address those security vulnerabilities. So IoT Device Defender. And then finally, now that we've got devices that are sending messages at scale. They're secure, and we know that they're in a good health state from our device defender perspective. We actually want to start doing analytics on this. And this is where IoT analytics comes into play. So it allows us to essentially easily start to act or analyze IoT data all the way from ingest through data enrichment, transformation, storage, and then be able to present this to downstream applications for consumption. So the first part is channels. So a channel is nothing more than the ability for IoT analytics to say, I want to have a particular IoT topic as an ingest point. Any messages I see appear on that topic are going to be considered messages that I want to ingest. It can also be other third-party services, such as S3 or even Kinesis, to be the ingest point. And by using APIs, you can essentially send those values into AWS IoT analytics. Once they're actually in there, then we have the pipelines where we're actually doing the enrichment, transformation, and cleansing of data. So imagine you getting multiple streams, and I'm getting metric data here, I'm getting imperial units here, and I want to sort of normalize all these to SI units. That's where channels or pipelines can come into play. So essentially allows us to take a look at data we know to be erroneous. We can sort of strip that out. We can transform information, or we can actually generate new values based on existing values that we see in the messages themselves. We then have data stores, and this is plural. So that enriched and transformed data is sent to a time series database that you basically set the size of what you want your retention to be, and the data is available there. The other alternate path, which is in play, is that it's going to be the raw data, because essentially you always want to ensure that you have the raw data that's available for use. We then create data sets on top of this, and data sets are essentially an endpoint, again using sort of SQL-like language, that will query that time series database and present essentially a subset of values back to here. It can be something such as, provide me all the temperature values normalized or averaged for the last 24 hours on this particular fleet of devices. The key thing about data sets is now they're now an endpoint that can be used by other downstream applications. One of those is Amazon QuickSight, so the ability to essentially visualize what's coming off of data set directly onto a QuickSight dashboard, but also be able to send this down to Jupyter notebooks. So if you are doing things such as machine learning or other types of inference inside of Jupyter, Jupyter notebooks inside of SageMaker, is you can send that data down to there. Essentially, do the cell run or the run command. It will reach out to analytics, pull the values down, and then do the local inference there. So we've spoken about basically end-to-end the core blocks. We need to be able to get data from the devices. So we're talking about the Amazon FreeRTOS, AWS Greengrass endpoints, getting this into the cloud in a secure and scalable manner through AWS IoT Core, managing at scale, protecting those devices that now they are deployed, and doing analytics upon this. So it's a lot of building blocks from one perspective, but there's another approach also that developers can use to get started a lot quicker. And another one of the words is it gets rid of a lot of the undifferentiated heavy lifting of collecting that data all the way through the other end. And that is through AWS IoT one-click. Has anybody used the one-click buttons before? Does anybody have a dash button from Amazon.com? Okay, a few more people here. So essentially the one-click button, and this is the enterprise button, essentially is in the same format as a dash component. But what it allows us to do is to essentially, as a developer or as a company, procure these devices. So I can acquire either a Wi-Fi connected device, which is what the IoT button here is, or the one that's from AT&T, which is the LTE-M type of device, which doesn't use Wi-Fi but uses the AT&T network, so it can be used in areas where it's a lot more constrained, oil fields, manufacturing facilities, and such. Once we have actually provisioned to procure the devices, we can then configure and deploy them. So essentially, we claim the device into our account, and then for every device, we can create a project and a placement for how devices want to interact, other attributes we want to put with those. And then on the back end, once a button is pressed, is that we'll take that message in and send to a downstream Lambda function, which is going to be our serverless code, which is going to then take some type of interaction on that. As this is now going and you've got devices that are placed for different projects, different locations, or whatever, you can now start to extract reports in regard to things such as, how many presses have I had? Single presses, double clicks, long presses, battery life, these types of things. So essentially, IoT one-click takes everything from getting that event at the very beginning, a button press, all the way through essentially being able to do the insights or action, the attachment of that Lambda function through a single service and process, without having to sort of put all the different components together. And so we're going to do a couple quick demos here, showing the sort of IoT components. So the first thing is that we're going to talk about a conceptual thing that we've got an assisted living facility that we want to have our residents be able to check in and see what's going on. So the first thing that we're going to do, we're going to give every one of the actual residents an actual IoT button. Whenever they go to a particular location, they click it once, and that is going to trigger a function which is going to update essentially their status. What's going to happen is that event, that Lambda function, is essentially going to publish to a couple different things. One is going to be to IoT core, so we get an immediate update, and then also to a DynamoDB database, where an API call that our single-page application that's hosted in S3 is going to actually show that sort of an update on the overall status. And then we're going to show that if somebody doesn't just want to check in, but they've got a problem with one of their appliances in their house, they can do a long press. And we're going to use a couple other Amazon services, including Connect, to actually initiate a call out to the person onto their phone. And they're going to use natural language processing to actually interact with the service to schedule an actual maintenance event or appointment. So with that, let's go ahead and hope the demo gods are working with us today. And just bear with me for a quick second here while I get this set up. The Wi-Fi has been flaky in certain areas on this laptop. Okay, so essentially what we have here is just a quick dashboard. And the top is essentially the resident status for a couple of our residents, Ms. Lovelace and Mr. Turing. And when I actually push the button on the device here, single click, it's going to update their last checked in. I just did the one on Alan because I wanted to verify that things were operational. So we'll start the process on the AT&T button instead. So you won't be able to see it, but this takes about 30 seconds from end to end to establish a connection to the network, publish the message, and then have that actually sent over to AWS IoT one-click for ingest. And it's blinking, blinking. And once that's done, what we should see is that Ada has been checked into her room or wherever she's at. So now while that's happening, we'll do this with the Wi-Fi button for Alan. And we sort of set the timeout here so that it quickly expires. So again, we do a quick press on the button. We're looking for blink, blink, blink. We get a green light, which indicates that the message has been sent. And then essentially it's publishing to an MQTT topic that our application is then shown that we've got to check in. And there's the one from Ada that she just also got checked in too. So that's all good and good. You can basically have a dashboard of the status of residents. But now I've got a problem with my refrigerator. So I'm going to do a long press here, which is going to trigger a different type of interaction. It's actually going to make a call out to me on my registered phone. I got a call coming in here.
Hello. This call is from the Silver Linings Concierge. If you didn't mean to have me call you, you can simply hang up. Now, how can I help you?
I need help.
Okay. Which appliance are you having trouble with?
My refrigerator.
Sure. What day should I schedule your service call?
Sunday.
At what time on August 5th, 2018?
9 in the morning.
9 o'clock is available. Should I go ahead and book your appointment?
Yes.
Okay, your appointment has been booked. Thank you for calling the Silver Linings Concierge. Goodbye.
Okay, so just a quick interaction there showing that we're using IoT in the back end. We're using one click, which gets rid of a lot of the components we have to deploy to basically have a workload or a process that is, interaction and is natural for people. It's very easy to tell somebody to press a button once if you want to check in, long press if you want to have somebody call you. And this way we're using an automated mechanism to do this and go through that process. And this can be applied for a lot of different use cases that are out there. All right, so any questions on that demo there? All right, great. I'll get to this as a quick second here, so let me pop back over. And so essentially, just to pop back over to here for a second, just wanted to go through that, we're essentially showing the end-to-end components for IoT. And in the demo, we're actually showing how we're using IoT along with other AWS services. And that's a very common pattern that we see, is that you may want to be able to collect messages in one system, IoT, send those over to another existing system or something else that's built inside of AWS, something on EC2, it's going to be serverless, whatever, to actually act upon it from that perspective. But I just want to sort of call out that from a building blocks perspective, we've got everything that can help you design, build, and be successful with the workloads, from the actual physical devices themselves all the way through messages at scale that you can take insight upon. So if you're actually interested in getting to know more about AWS IoT, besides the documentation, a couple different resources that are out there. And you'll have access to this slide deck once it's published after the summit here. But we have a workshop out there that's focused on AWS IoT. And what this will actually go through is the use of AWS IoT Core. It'll also show you how the backend lambdas are being used to ingest a message or take in a message as an event and do some processing on this. And then using simple notification service as that sort of downstream for making notifications. Now, if you want to take that from more of we're sort of playing with the services and see sort of an actual use case, is we also have what we call some solutions out there. One of these is called the Internet of Tracking. And again, you'll have this in the slide deck. Let me build this out. But essentially what this is going to be a video that's going to walk through essentially a use case of how do you track things at scale. I've got tractor trailers, shipping containers, pallets, whatever, that I want to track. And how you can take that particular use case or business outcome that you want to achieve, and such you have this applied and put into an actual mechanism such as a dashboard showing you all these information with using AWS IoT in the backside. So things such as, where's the location, other things that you may want to actually trigger and take a look at. So with that, that's basically the presentation of edge to analytics, all the core building blocks here. I would ask that if you'd please go ahead and fill out the session feedback here. And if anybody does have any questions, I'm happy to take them. I got a mic up here that I can activate. And if you want to raise a hand, I can answer some questions here. If not, I'll definitely be available outside for about 10 to 15 minutes after this particular session to answer anything that you want on a one-on-one basis. Anybody have any questions that you want to answer? Probably the best thing if you want to come up here and just sort of line up. Looking for the on button. Oop, I may need some help here.
I could just ask you to repeat.
That'd be fine.
So one of the challenges with the LTE connection is you pay for the megabytes. So anything about management of bandwidth, when you do firmware download, you'd like the local replicate so you don't have to download the image, anything to support that to manage bandwidth on LTE?
Sure. So the question is around things such as LTE or bandwidth that's very expensive. How do you manage things where you may be doing firmware updates or this types of things? How do you sort of, thank you, deal with that? And there's a couple different approaches. Greengrass is a great approach if you've got common devices that are local that have the same firmware. Instead of downloading to each individual device, download the Greengrass core and then let the devices talk to Greengrass, again, because you can have that local file system to actually do the type of connectivity. The other thing is basically cutting out message sizes. If you've got a very descriptive JSON document with temperature, just replacing that with T:, and knowing that that's going to be a temperature value, significantly reduces the overall size of messages overall. The other key thing we see customers doing is that you over-index on how many messages per second or per minute that you need. One customer was actually taking a look at water boilers, and they wanted to have a new message every 5 seconds with the current temperatures. And we actually took a look at what the sort of ramp time is, that if there's like an event where a boiler is either going over pressure or under pressure, it was measured in tens of minutes instead of seconds. So by actually being able to reduce that from 5 seconds to 1 minute, is we were able to actually help them reduce the cost of their messages by by a factor of 20. So there's a lot of different patterns from that. What I'd probably say is you want to take a look at each individual one and go from there. Other questions? Yes, sir.
Greengrass, that can run on one node, on each node, or can you have multiple IoT nodes talking to one Greengrass that goes to the cloud?
Got it. So the question is around Greengrass, and is it basically one node or multiple nodes, and can you have just one device talk to it or multiple devices talk to it? So the normal deployment pattern for Greengrass right now is that it is a single core, but you can actually deploy multiple cores to an environment. And you can have hundreds of devices connecting to an individual Greengrass core. So a common pattern there may be that, let's say you've got a factory and it's got 3 different zones, and you can break them up accordingly. You may deploy 3 Greengrass cores, one for each zone, and then all of the devices that want to communicate for that particular zone would connect to their local Greengrass core.
Can they connect through Bluetooth?
And the question is, can they connect through Bluetooth? Not natively. So again, we're going to provide you with MQTT connectivity, but we can also show you different patterns for alternate path connection mechanisms to Greengrass. Because Greengrass is essentially running as a process on a Linux box, there's nothing saying that you can't have other processes that are running right alongside that are doing that sort of connection for other types of protocols, and then in turn talking to Greengrass. So imagine that you have a process that is listening on a local Bluetooth connection, 6LoWPAN, some other type of network that is then doing the translation inside of a separate process with a connectivity to Greengrass. The one thing to be aware of there, though, is that if you're abstracting out multiple devices, when they're having a single process connecting to Greengrass, that is going to be the surface area from a security perspective of all Greengrass is going to know is about this one device connecting, not everything downstream. Yes, sir. So the question was, is Greengrass only available for embedded Linux? Got it. Okay. Yeah, so the question is, what is Greengrass available for? What is FreeRTOS available for? So Greengrass today is available for any type. Essentially, we've got certified platforms that it'll run on. It'll run on Raspberry Pi, Amazon EC2. Essentially, any Linux kernel 4.4 or greater has got the C group capability that's necessary for Greengrass to run. We do have a certification process in place. We also have a lot of customers that are running this on their own distributions, Ubuntu and others that are running perfectly fine. So Greengrass is always for that Linux type of environment. It could be Raspberry Pi, it could be other types of devices that are running Linux. Amazon FreeRTOS is more for the embedded chipsets themselves. So this might be from ST, Microchip, Nordic Semiconductor, where you're essentially writing FreeRTOS code that is talking directly, basically it's C++ code that you're compiling and running that mechanism there. But FreeRTOS can also be Greengrass-aware devices, meaning that they've got the modules to do the connection to a Greengrass core and understand the certificates and that connectivity mechanism. Yes, sir, I'll get to you. Is it available on iOS? It is not available on iOS since iOS does not run the Linux kernel. It could run on Android because Android does use a Linux kernel underneath there. One thing from a Greengrass perspective is it does run as a privileged or as a root process. And it has to do that because it is helping manage the underlying security constraints for the Lambda functions that run, being able to do a lot of the C group capability for those types of components.
Do you have any plans to make it available on iOS?
I don't know of any plans, but again, this is great feedback that we'll feed back to the service team. And if you want to talk a little bit later about this, I'd like to understand the use case a little bit better. Awesome. You, sir. Yep.
So essentially, Greengrass would require higher computational ability than RTOS. RTOS is for endpoint, and Greengrass is for gateway.
Yes, so the question is, computationally, Greengrass, does it require more? What is it basically designed for? And yes, it is more for gateway type of components. We see this where customers are deploying these where they want to have, like I said, a gateway to different environments. It may be a set-top box in a house. It may be the interface between an internet connection into a manufacturing process line, or where you simply need to have more horsepower that you want to do inference at the edge. We have customers that are running this on things as small as Raspberry Pi type of capabilities, up to multi-core environments where they're running multiple Greengrass cores on high-end compute server type environments.
And that probably is motivated by the number of concurrent client connections maintained. So RTOS, you also mentioned, would have a former client component for Greengrass, right?
Yeah, so the follow-on is that Greengrass is more for a lot of devices connecting to it and doing things. Yeah, FreeRTOS and Amazon FreeRTOS is more about it is making a single connection normally to either a Greengrass core locally or up to AWS IoT core. And that might be on an intermittent basis also as necessary. But yeah, it's definitely for the more constrained devices where even things such as the power budget for setting up a TLS connection can have a substantial impact on battery life.
Very quickly, last thing. So the gentleman was asking about Bluetooth connectivity.
Yep.
Rather than what? We were presuming Wi-Fi? Is that what the presumption was?
Yep.
Okay, so in that case, MQTT requires Wi-Fi?
MQTT requires TCP/IP.
Yeah. Okay.
Yep. So if you can run a TCP/IP protocol on top of a layer 2, such as Bluetooth, things such as that, LoRa, other types of protocols, you absolutely can still do that. And that's where some of the other modules are coming out from that perspective. All right, probably one or two more questions. Yes, sir.
So excited to one of the answers that you gave about the zoning factors, right?
Yes.
Having different Greengrass running and multiple devices connected to it. Can the same device connect to multiple Greengrass environments just to be from a clustering perspective on the Greengrass side if you have like a lot of devices in the factory?
Sure. So the question is, I spoke about zoning where lots of devices might be connected to one Greengrass core, another set of devices to another one. And can you have that where the device may be able to connect to multiple Greengrass cores and connectivity? From a FreeRTOS perspective, not today, or not easily today because you have to manage essentially dual connections. But you could do this from other types of applications. Today, currently, you have to actually manage the flow of who you're communicating with. So I would say that's a big ask from customers is how do we actually provide higher availability or reliability for Greengrass? Something the service team and the product team is definitely well aware of. Yes, sir, back there.
Could you help explain or elaborate a little bit on the authentication piece where you have to manage certificates? So AWS provides the certificates and you download it to the devices themselves?
Correct. So this is going a little bit deeper into how the sort of certificate management process is. And actually, we're pretty much in time. I want to be cognizant for the next session. If you want to, after this question, we'll take it outside. So essentially, there's a couple different approaches there. Is that we provide you the capability of making API calls to essentially generate a certificate and download the actual public key, private key, and the certificate itself, so the X509 certificate, which you can then, a device could then, embed directly into it and manage that perspective. Works well for certain use cases. Customers that normally have got security infrastructure in place, such as their own PKI CAs, will normally elect to actually use a certificate authority that they register with AWS IoT, where they can still generate all their certificates locally. Maybe not even actually send them up to AWS IoT initially, but just put those in devices, and then use the just-in-time provisioning process or a just-in-time registration process to essentially automate that. But there's a lot of flexibility for how you actually manage key credentials from that perspective, and something that we like to dive deep with customers on for here's what we've seen other customers do, Here's things you never want to do, such as shared certificates or ones that are shared across multiple components, and then go from that perspective. All right, great. Well, thank you so much for your time, and enjoy the rest of the summit.